This chapter details the methodology applied in the research, including the overall system architecture and specific descriptions of each component module. The RAG system is built upon the combination of an offline phase based on HippoRAG2 and an online phase refined to suit the specifics of the Vietnamese language. Figure presents the overall system architecture, comprising two main sequential phases. The offline indexing phase implements the HippoRAG2 method to build a knowledge graph from Vietnamese text through four processing modules: document segmentation, triple extraction via OpenAI, synonym detection using multilingual embedding similarity, and knowledge graph construction. The online retrieval QA phase is refined and improved with hybrid retrieval combining BM25 and embedding, different from HippoRAG2 which only uses dense retrieval, LLM-based triple filtering, passage re-ranking based on triple support, replacing the complex PPR algorithm, and answer generation to suit Vietnamese and reduce computational complexity. This architecture effectively combines structured information processing, triples from the knowledge graph, and unstructured information, text passages, to enhance information retrieval and answer generation quality. Notably, the use of multilingual large language models optimized for Vietnamese in key steps helps the system effectively handle local language and cultural characteristics. In the offline indexing phase, the core task is to build a long-term memory system by constructing a knowledge graph, kilogram, from input text documents. This phase is considered the foundation for the entire proposed RAG system, critically impacting the quality and performance of future information retrieval operations online phase. The component modules in this phase cooperate closely to systematically and structurally extract, process, and organize information. The goal is to create a rich, diverse, and flexible knowledge representation, ready for efficient querying in the online phase. Specifically, in this offline phase, the research focuses on building a knowledge graph comprising two main types of nodes: phrase nodes and passage nodes. Edges. Here is a detailed description of each module in the offline indexing phase. Document segmentation is an essential initial step in the memory building process. The goal of this step is to break down original text documents into shorter passages, where each passage should carry a relatively complete and independent logical meaning. To achieve this with high accuracy, the proposed system leverages the power of large language models, LLMs, specifically the Quen 1.5b instruct model. The segmentation process begins with the LLM deeply analyzing the overall structure of the source document. The model identifies structural components such as major sections, chapters, headings, paragraphs, and other text organizational units. A crucial difference compared to traditional methods is that the LLM does not rely solely on surface cues like punctuation or a fixed word count to segment. Instead, it identifies boundaries between passages based on changes in topic, flow of ideas, or context presented in the text. The result is that each generated passage is of moderate length, sufficient to contain a complete meaning, but not too long to complicate subsequent processing steps. An important requirement is that the segmentation process must ensure that each resulting passage retains enough context to be understood relatively independently, even when separated from the original text. Effective document segmentation plays a foundational role for several reasons. First, appropriately sized and semantically coherent passages facilitate more efficient operation of the triple extraction, OpenAI module in the next step. Second, it helps ensure that important contextual information is not lost or arbitrarily cut when documents are broken down. Third, well-segmented passages will be more easily indexed and accurately retrieved when users perform queries in the online phase. Finally, segmentation also helps eliminate noisy or irrelevant information, helping the system focus on core and important content. Compared to traditional segmentation methods, which often rely on fixed heuristic rules, e.g., sentence breaks, fixed word counts, special characters, the proposed system's LLM-based approach offers significant advantages. LLMs have a deep understanding of context and the underlying meaning of text, not just surface structure. This allows for the creation of passages with much higher semantic coherence. Moreover, this method is highly adaptable to various document types, formats, and writing styles without needing to redefine rules. It also significantly minimizes the risk of breaking up ideas, concepts, or logical relationships that are presented continuously in the original text. Consider the original text about the benefits of some fruits. The document segmentation module using LLM will analyze the semantics and identify distinct topics, creating coherent passages as follows. The result is passages focused on individual fruit types or general benefits, facilitating detailed information extraction and subsequent retrieval. The main purpose of this module is to perform open information extraction, i.e. to extract structured knowledge units, called triples, from the text passages segmented in the previous module. In this research, it is assumed that the segmented passages are simple and coherent enough for direct extraction. Specifically, the system uses a large language model, such as Qwen or the improved Qwen 2. 5-7b instruct, to perform the OpenAI task. This process aims to transform latent information in unstructured text into a structured, explicit knowledge form, ready for integration into the knowledge graph, kilogram. The choice of a model like Qwen is considered capable and suitable for this task, balancing performance and computational cost. The triple extraction process begins with the LLM deeply analyzing the semantics of each passage to identify key events, relationships, and attributes mentioned. For each identified event or relationship, the LLM generates one or more triples in the standard format: subject, relation, object. For example, from the sentence Chewy-chan Ukali, banana contains a lot of potassium, the LLM can extract the triple Chewy, cha, Kali. After extraction, these triples often undergo a normalization step to ensure consistency and facilitate subsequent processing. For instance, variations of the same entity or relation can be mapped to a single canonical form. Finally, each extracted and normalized triple contributes to building the kilogram. The subject and object of the triple will form two phrase nodes if they don't already exist, and the relation will create a directed relation edge from the subject's phrase node to the object's phrase node. A key characteristic of the proposed system is the application of a schema-less open kilogram construction method. This means the system is not limited by a predefined set of relation types, schema. Instead, it can extract and represent any type of relation that the LLM discovers in the text. This approach offers high flexibility, allowing the kilogram to represent the diversity and richness of information in the real world, unlike traditional kilogram systems that often require a rigid schema. Using LLMs for OpenAI offers significant advantages over rule-based extraction methods or traditional machine learning models. LLMs have a deep contextual understanding, allowing them to extract complex, implicit, or context-dependent relationships more accurately. The schema-less approach makes the kilogram flexible, easily extensible, and capable of integrating information from various sources. LLMs can also better handle complex sentence structures, linguistic variations, and subtle expressions that rule-based methods often miss. Overall, this method promises higher accuracy, better handling of complex text, no longer requiring costly manual rule building, and is highly adaptable to different domains and languages. Consider the passages segmented in Module 1, T Passage 2, DAO T Passage 3, Cam T Passage 4, Li Ich Chung. Each of these triples will be used to create phrase nodes, e.g., Chewy, Kali, DAO, Pectin, Cam, Vitamin C, and relation edges, e.g., Cha, Jup, Lan Gun, HTR, in the kilogram. After triples have been extracted and corresponding phrase nodes created in the knowledge graph, a challenge arises from linguistic variability. The same concept or entity can be referred to by multiple names or phrases in different parts of the document or across different documents. The synonym detection module is designed to address this problem by employing word sentence embedding techniques. The objective of this module is to automatically identify phrase nodes in the knowledge graph that represent the same concept, i.e., they are synonymous, and create links, synonym edge, between them. The proposed system uses a powerful embedding model, for instance, sentence transformers paraphrase, multilingual, MNET, base, v2, chosen for its effective processing of Vietnamese data and multilingual support, which is suitable for the research scope. The operation process of this module is as follows. Integrating the synonym detection module offers several significant benefits. First, it helps overcome linguistic diversity, allowing the system to recognize and link different expressions of the same concept. Second, it connects scattered information in the knowledge graph by creating logical links between similar pieces of information represented by different phrases. This directly improves information retrieval capabilities, increasing the recall of search results, as a query for one term can automatically expand to include synonymous terms. Furthermore, the use of multilingual embedding models like Paraphrase, Multilingual, MNET, Base, V2 also opens up multilingual processing capabilities, allowing for the linking of similar concepts expressed in different languages, e.g., DAO and Apple. Suppose the kilogram contains the following phrase nodes with their embeddings, calculating cosine similarity, with a threshold of 0. 9. The system creates. The final module in the offline indexing phase is knowledge graph integration, dense sparse integration. This module does not perform additional complex processing but focuses on completing the structure of the knowledge graph, kilogram, by ensuring all components created from previous modules, passage nodes, phrase nodes, relation edges, synonym edges, are logically and fully connected. In particular, this module emphasizes creating contain edges to clearly link the full context, passage node, with the core concepts, phrase node it contains. The main process of this module includes the creation of contain edges provides important benefits. Link context and concepts. It creates a clear bridge between the full text representation, passage node, and the structured knowledge representation, phrase nodes and relation edges, allowing the system to easily transition between these two forms of information during retrieval and reasoning. Support diverse retrieval. When querying, the system can start from a phrase node, concept, and easily find all passage nodes, contexts, containing that concept via reverse contain edges, or vice versa. Foundation for graph algorithms. The complete kilogram structure with diverse node and edge types provides a solid foundation for applying more complex graph algorithms if needed, such as label propagation, node clustering, or variations of PageRank, like PPR in original HippoRAG, for deeper analysis and reasoning on the graph. At the end of Module 4, the offline indexing phase is complete, resulting in a rich and well-structured knowledge graph, ready to serve complex information retrieval requests in the online phase. Consider the components available from previous modules. Module 4 will focus on creating contain edges. Upon completion, the kilogram will have a complete structure, tightly linking passages and the concepts facts contained within them, ready for the online phase. After building the knowledge graph, kilogram, and indexing the text corpus in the offline phase, the system transitions to the online phase to process user queries and generate answers. The main goal of this phase is to efficiently retrieve the most relevant information from both the kilogram and the text corpus, then synthesize it into a high-quality context to provide to the large language model, LLM, for generating the final answer. The proposed method focuses on combining information from passages and triples, using core facts to refine and filter passages, while avoiding the complexity of extensive graph propagation algorithms like PPR. Figure presents the online retrieval QA phase workflow, featuring a dual-stream processing architecture. The system takes a user query and knowledge graph as inputs, then processes them through Module 1's hybrid retrieval to generate raw passages and raw triples. The triple stream undergoes LLM-based filtering in Module 2 to produce high-quality filtered triples, while the passage stream flows directly to Module 3. Both streams converge at Module 3 for passage re-ranking based on triple support, creating ranked passages that serve as factually grounded context for Module 4's answer generation. This design ensures the final Vietnamese response combines both semantic relevance and factual accuracy. The first module in the online phase acts as the gateway for user queries, performing the initial information retrieval from two main data sources prepared in the offline phase, the passage store and the knowledge graph, kilogram. The objective of this module is to collect a set of potential candidates, including both text passages and information triples, that are likely to contain information relevant to the query. To achieve good coverage and leverage the strengths of different retrieval methods, this module implements a dual retrieval, or hybrid retrieval strategy. Specifically, the output of this module is two initial sets of candidates, raw passages and raw triples, laying the groundwork for subsequent filtering and refinement steps. Suppose the user queries, what are the benefits of apples for digestion? Triple retrieval, top end 50. The result is two lists, raw passages, primarily P2, and raw triples, focused on apples and digestion, ready for modules 2 and 3. After collecting a large initial set of candidate triples, raw triples, from module 1, the next step is to refine this set to retain only the core, reliable, and most directly relevant facts to the user's query. Module 2 performs this crucial task by using a large language model, LLM, as an intelligent filter. The main goal of this module is to transform the list of raw triples, which may contain noise, irrelevant information, or low-level facts, into a smaller, higher quality set called filtered triples. This set will serve as the gold standard or core facts for subsequent processing steps, especially in ranking and filtering passages. The operation of Module 2 is as follows: prepare input for LLM. The system gathers the retrieved raw triples and the original user query. This information is formatted into a clear prompt for the LLM. The prompt asks the LLM to evaluate the relevance of each triple to the query and select the top m most important triples from the input list. Detailed prompt example, where original user query, list of raw triples, and m will be replaced with actual values. Using large language models, LLMs, as triple filters offers several advantages over simpler rule-based or threshold-based filtering methods. Firstly, LLMs have a deep contextual understanding, allowing the model to recognize the true intent behind the query and assess the semantic relevance of each triple more subtly. Secondly, LLMs offer high flexibility, as there is no need to predefine rigid filtering rules and they can adapt to various query types and application domains. Finally, thanks to their strong reasoning capabilities, LLMs can eliminate noisy information and retain truly important facts, thereby creating a high-quality, semantically rich set of filtered triples that serves well for subsequent processing steps. The filtered triples result plays a crucial role in directing and enhancing the quality of subsequent processing steps in the pipeline, preventing the redundancy of information irrelevant to the query. Continuing with the query, what are the benefits of apples for digestion? Assume raw triples, top N50, contains triples such as, using the prompt example above with M5, the LLM, Quen2. 5-7b will analyze and select the triples most relevant to the digestive benefits of apples. The resulting filtered triples might be, the LLM has eliminated triples about apple peel, fruit type, bananas, oranges, and retained the core facts about apples, fiber, pectin, and their role in digestion. This set of filtered triples will be used in Module 3. This module is the core innovation of the proposed retrieval method. Instead of relying solely on direct query passage similarity, like standard RAG, or complex graph propagation, like HippoRAG, this module re-ranks the initially retrieved raw passages based on their relevance to the high-quality filtered triples identified in Module 2. The goal is to prioritize passages that not only match the query keywords or semantics but also strongly support the core facts deemed most important by the LLM filter. This approach aims to improve the precision and relevance of the final context provided to the LLM for answer generation. The process is as follows: this triple-based passage ranking method offers several advantages. It leverages the structured knowledge, triples, filtered by the LLM to refine the selection of unstructured text, passages. This helps ensure that the retrieved context is not only topically relevant but also factually aligned with the most important aspects of the query. Compared to standard RAG, it adds a layer of factual grounding. Compared to complex graph methods like PPR, it is computationally simpler while still incorporating graph-derived information, triples, into the ranking process. Continuing with the query and previous results, calculating relevance scores using a simplified co-occurrence embedding method re-ranking based on these scores, P2 will be ranked much higher than P4. Selecting top P3 passages, the system will likely select P2 as the top passage, potentially followed by other less relevant passages if P2's score is significantly higher than others. The final ranked passages set will be highly focused on the Apple passage that directly addresses the query based on the filtered facts. This is the final module in the online phase, responsible for synthesizing the retrieved information and generating a coherent, comprehensive, and accurate answer to the user's original query. It leverages the power of a large language model, LLM, often referred to as the generator or reader in RAG terminology. The process involves the quality of the final answer heavily depends on two factors: the quality of the retrieved context, ranked passages, and the capabilities of the generator LLM. By using the proposed retrieval pipeline, modules 1 to 3, that filters triples and ranks passages based on these core facts, the system aims to provide a highly relevant and factually grounded context to the generator LLM, thereby reducing the likelihood of hallucinations or irrelevant information in the final answer. Continuing with the query, what are the benefits of apples for digestion? This answer directly addresses the query using only the information provided in the relevant passage P2, demonstrating the effectiveness of the RAG pipeline in generating contextually grounded responses. This chapter presented a comprehensive methodology for developing an improved RAG system optimized for Vietnamese question answering through knowledge graph integration and advanced retrieval techniques. The offline indexing phase successfully implements and adapts the HippoRAG2 approach for Vietnamese text processing. Through 4 modules: LLM-based document segmentation, OpenIE triple extraction, multilingual synonym detection, and knowledge graph integration, this phase builds comprehensive knowledge representations from Vietnamese text, creating a foundation with both structured knowledge, triples, and unstructured information, passages. The online retrieval QA phase introduces refinements specifically tailored for Vietnamese language processing. The hybrid retrieval strategy combines BM25 and embedding-based approaches for improved coverage. LLM-based triple filtering identifies relevant facts, while passage re-ranking uses filtered triples to prioritize contextually appropriate information. These refinements address computational complexity while maintaining effectiveness, offering a practical alternative to complex algorithms like personalized PageRank. The methodology addresses key limitations in existing RAG systems: limited retrieval method combination, diverse information processing challenges, and insufficient Vietnamese language support. By incorporating multilingual large language models throughout the pipeline, the system handles Vietnamese language nuances effectively. The main contribution is developing a complete Vietnamese RAG system that combines structured and unstructured information processing, providing a practical solution for intelligent information systems serving the Vietnamese community. Chapter 4 will present experimental evaluation of the proposed system, testing each component on the 6MQA dataset and comparing against traditional RAG baselines to assess the contribution of each improvement to overall performance.